Hi, my name is David Bombara, and today I will be discussing experimental characterization and modeling of the self-sensing property in compliant twisted string actuators. I did this work at the Smart Robotics Laboratory in the University of Nevada, Reno, and I would like to thank my co-authors, Konda and Dr. Zhang. This work was also published in IEEE Robotics and Automation Letters. In this presentation, I will answer three main questions. Firstly, why is self-sensing important for twisted string actuators? Next, how was the experimental characterization and modeling conducted? And finally, what are our results and also our limitations of our strategy? So to start off, why is self-sensing important? The twisted string actuator is a mechanism that can generate linear contractions by rotating a motor. And what's interesting about this is that you can actually generate high output forces with relatively low input torques. Essentially, the strings act as a gear with a high transmission ratio. TSAs also have high stress output, high efficiency, and high linearity. Strains are typically 30 to 40%, and there are lots of robotic applications. Some of these applications are exoskeletal devices and assistive devices, bio-inspired robots, soft robots, tensegrity robots, and even haptic devices. In our lab, we have worked on a self-sensing compliant TSA. Typically, TSAs are realized with stiff strings, but our strategy is to replace those strings with these strings known as SCP strings, and these are both conductive and compliant. SCPs are also interesting in that they can contract or expand due to heat, so they can be used as actuators or artificial muscles in and of themselves. So our strategy has been to predict the length of the actuator by measuring the resistance, and this is how we obtain self-sensing. The reason that we're interested in self-sensing is because to measure the length of a TSA, you need a position sensor that is bulky and possibly rigid, or one of the two. So the benefits of self-sensing are that if we can eliminate the need for that position sensor, then we can make robots that are actually more compact, flexible, lightweight, and compliant. So all these good qualities could be realized in TSA-driven robots. So currently, it's difficult to realize a TSA-driven robot that has that closed-loop position control. In our lab, we have made some progress on the self-sensing TSA. So previously, we developed a hysteresis models for steady-state resistance and length correlations for low cycle counts. We also explored the dual heating and twisting property. As I mentioned, SCPs can actually contract under applied heat, but we did not model or characterize the transient or long-term behavior of the actuator. And this brings me to the next section. Our experimental setup and procedure was conducted in an automated way. So we first determined parameters. So we set the load, twisting range, step size, and wait time. And then we set the experiment and then collected the data automatically. We kept a constant load of 350 grams because the TSAs are compliant, so they're very sensitive. Their length is very sensitive to changes in load, and the twisting range was found to be the optimal range for the resistance length correlation, and our step size was constant, so we rotated 5 turns at a time, waited a given amount of time, and then kept rotating. Our modeling approach is a sum of 3 terms, and each term represents a particular behavior of the resistance measurement. So the transient term captures that decrease in the resistance when the length stays constant. And then the hysteresis curve captures the behavior where the resistance on the ascending lengths is different from the resistance when the length is decreasing. And then finally, the creep term captures a steady overall increase in the resistance over time. And this is a data-driven approach, so we didn't consider a physics-based model because it was actually more complicated than we found to be practical. Our transient decay was modeled as a polynomial of logarithms. We found that transient decay depends only on the time at which the motor has been at rest. So the transient decay did not depend on the current length of the TSA or the amount of time that the motor waits between rotations. So this is good because it enables a more generalized model where we only need to know the time and then we can predict the transient decay. The next term is the hysteresis. So we used a rate-dependent Prandtl-Jedlinski model. What this is a weighted sum of backlash operators, and the width of each backlash operator depends on the rate at which we change the length of the TSA. So therefore, the shape of the hysteresis curve shown on screen changes depending on the rate of input. And the graph shown on screen, I should mention, only depicts the steady state resistance values. So that transient decay is not shown in this graph. Next we have creep. So creep we modeled as a sum of first order difference equations, and then we added a term that was proportional to the length. So the creep was necessary to be modeled because, as you can see in this graph, we twisted the strings for 2.5 hours and we saw a steady increase in the resistance measurement, whereas the length stayed approximately the same overall between cycles. To obtain our self-sensing model, we have to do some manipulation of the models I just mentioned, because what we're interested in is predicting the length given the resistance and given the time. So first we measure the we measure the resistance, and then we subtract the resistance that we expect is due to transient decay and due to the creep. And then after we obtain that result, we invert it using an inverted hysteresis model, and this is what gives us the expected length only by measuring the resistance and time. And the creep model does take length as input, but it takes the previous length as the input, not the current length. So this model this strategy is realizable from a controls perspective. So next, what are the results and limitations of our self-sensing strategy? First, I want to show the results for when we predict the resistance given the length and time. We used 2 different wait times to identify the model, and then we validated our model on 3 different wait times. So you can see that the modeling identification errors are obviously lower than the modeling validation errors, but overall, even the validation errors are very small. So the average validation error was only 0.03 ohms, so that's less than 1% of the total resistance of the actuator. Our modeling results for the self-sensing model are also very good, and there's not a lot of difference here between the identification and validation, which is, from a practical standpoint, is very good because predicting the length is more important than predicting the resistance in an actual robot. Our modeling identification errors were less than 0.03 centimeters, which is less than they were less than 0.03 centimeters, which is less than 0.3 millimeters. And as I mentioned, there's not a lot of difference between the identification and validation errors, and you can see that in the bottom right graph where I show the average errors for each wait time. In conclusion, we developed a model and we experimentally characterized a self-sensing compliant TSA. We accounted for 3 phenomena: transient decay, hysteresis, and creep. However, our model only worked for 1 loading condition, so in the future we want to develop a model that works for different loading conditions or possibly even unknown loads. This part of the challenge in developing that model that works for different loading conditions is that our model is not physics-based. So possibly if we developed a physics-based model, it would be more general and enable more, I should say, more robust control or predictions of the length. So in the future, what we want to do is we want to develop a feedback controller and validate it on a robot, perhaps a soft robot or a robotic finger or robotic hand. And so we want to drive the TSA to a desired length by only measuring the resistance and time. This concludes my presentation. Thank you so much for listening, and please let me know if you have any questions. Thank you.